So the differential equation we have for second order system will be again y being the input, x being the x being the output, and there are three system parameter we want to identify for the second order system, which is capital K, steady state gain, or we call static sensitivity. By definition, that would be the output unit divided by input unit. And then we have zeta, we define as damping ratio. There's no unit for this, it's a ratio. Then we have omega n, which is the natural frequency of the system. For unit consistency, the unit should be radian per second. Okay. So before, for first order system, if you remember the first order system, we have K and tau. K is steady state gain and determine how much the system amplify the input. Now we have the same K, so same meaning for second order system for K, but how about damping ratio zeta and the natural frequency omega n? Because first order system tau determine how fast, then how about zeta and omega n? Okay. When we deal with second order system, we always look at the characteristic equation first, and in other words, try to find if you either using the Laplace transform method or using the classic undeterminate coefficient method, you can get to the characteristic equation, which is square s squared plus m s plus 1, or sometimes people use this one. And based on this, we solve for omega s, which is this is what we call characteristic equations, and try to find the poles or characteristic roots. And s should be so here's the situation. For this, there are three possibilities for the roots. If zeta is greater than 1, so we will have two real roots, two distinct. Then let's say R1, R2. So the solution for this kind of differential equation, ordinary differential equation, will be a combination of exponential minus r1 t plus another exponential function exponential minus r2 t. But in this case, we have two distinct real roots. And of course, then we have equal to 1. So this term goes away. So s equal to minus r1, which is in this case would be minus zeta omega n, because you have two repeated real roots. So we don't have my writing yet. So repeated. And then of course there's another situations, damping ratio smaller than 1. So in that case, these terms smaller than 1, square root of minus values. So it's complex numbers. It's n times I. In other words, it's a conjugate pair. Complex. So based on the characteristic equations, we can have these three scenarios. And for first one, we call this is overdamp. This is critically damped. And this one should be underdamp. So from here we can determine, so what is the damping ratio for? It determined if you have oscillation or not, because if you have an overdamp situation, so the solution form for this situation, you will is two exponential function combined, and this one would be a plus bt still exponential function, but that will be with first one and the other one another linear base t times the exponential function. Again, still exponential functions. About the last one, if you remember in 340, the solution form will be exponential functions as well as sine and cosine function. So there's three cases here. One overdamp, critically damp, underdamp. So if you look at these three equations, you can see the only sine and cosine will be term here will show the oscillations. In other words, only for this situation right here, under damped situation, you will have oscillation. This is also exponentially decay, exponentially decay, exponential decay plus sinusoidal functions here. So based on this, we can say that damping ratio, what is damping ratio for? Again, K determine how much the system being the system amplify the output, the input. Damping ratio determine oscillation or not. And what's natural frequency? If it oscillate, determine the oscillation rate. Okay. So now let's look at the solution form. Since this is a standard first order system, let's say what's the solution form for the step input. Let's say step input will be step response x of t. In other words, y of t will be an amplitude with a step functions. So since like I said, this is a standard form, so the formula it will be given. It's already posted on Blackboard, so you can see you have three different situations. Overdamped, if there are two real roots, distinct real roots, minus R1, minus R2, automatically you can get to this form right here for step input. Critically damped, you have this form. Underdamped, you have this form right here. Okay, so I won't worry too much about the equation because these are formulas it will be given, but let's look at the shape or the response curve in terms of time on these equations right here. Three different cases here. So if I plot it, time in t, x of t. So when time goes to infinity, if this is both R1, R2 is a positive number, so minus R1 minus R2 are both negative numbers. This term goes away when time goes to infinity, so you have Ka. So simply I will get to this graph. K times A. Overdamp, I have these situations. Critically damped, I have this one. Underdamp, I have oscillation and decay. So this is first one, underdamped. Underdamped, D-E-P-E-D. So this one, critical dedamp. And this one here's overdamp. In other words, this is equal to 1, zeta equal to 1 greater than 1. This is between 0 and 1. Of course, what happened if damping ratio equal to 0? In other words, in the systems, there's no damping. No energy being dissipated. It's like a spring. So you will have so basically given a excitation, it will keep oscillating without stopping. It's like a simple harmonic motions. Let's make the scale a little bit up. Keep oscillating. Keep oscillating. No damping. Okay. In general, we like to have for a system to have faster response time. In this case, most of the system we want to design to be a underdamped situation. So we'll take a close look of the underdamped systems, and then we can characterize this underdamped with several value specification parameters. So let's do that again. So let me rewrite this equation. Damping ratios. So this is a underdamped. This is time, t in second, standard unit, x of t, steady state value, k times a. And we also want to find this value right here is peak time. Okay, so particular for control, we have several parameters to specify a control systems in terms of design. So first one, would be these so-called maxima overshoot. In other words, over the steady state values.